In the last video, we defined torque in a beginning of trying to describe how forces can make things rotate. And here we're going to look at objects that aren't moving or rotating, what we call static equilibrium. Turns out we can loosen that up just a little bit, but more on that in a future video. But for now, we'll just say we've got objects that are neither moving nor rotating. So what do we know is true about that? Well, if everything's confined to the xy plane, which is what we're going to limit ourselves to here, we know that the net forces have to add up to 0. So that separately means that the sum of the x components of all the forces acting on the thing have to be 0. The sum of the y components of all the forces acting on the thing have to be 0. And now, because we're saying and it's not rotating, the sum of the torques on it has to be 0. So let's go and see how that can help us out here. To start with, let's just go and take a look at a teeter-totter. So if you're playing a game of teeter-totter, let's say you got a kind of a big kid over here, kind of thrilled because the big kid is looking forward to sending the little skinny kid off into orbit. Now, the teacher looks on the playground and says, you know, that doesn't seem terribly fair. And so the teacher moves the fulcrum, the pivot point on the teeter-totter, to a point where it would be fair. All right, let's give some numbers to this, and then we'll take a look at how we can approach this kind of a problem. So let's say the big kid is 50 kilograms, the little kid is 25 kilograms. Let's say the length of the plank is 3 meters. And what we would like to know is how far over from the big kid should we put the fulcrum so that it'll balance. And while I'm at it, I'll dimension this distance here as L2. And also, we would like to know the magnitude of the normal force. We'd like to know the normal force that the fulcrum exerts on the plank. Okay, so first off, let's go and define ours. And we'll also, just for simplicity's sake, we'll make the plank itself massless. Okay, so we can make our system the kids plus the plank. And here, what you want to do is draw something called an extended free body diagram. So this differs from a normal free body diagram in that you don't bother drawing a dot anymore. What you do is you draw a little cartoon of the thing. So I'm redrawing the big kid and the skinny kid. And now what we'll do is we will go ahead and draw in the forces at their points of application. So we will have a force of gravity acting here, call that Fg1, and it's being applied at the heavy kid. And we'll have a force of gravity acting here, Fg2, acting on the skinny kid. Now, if those were the only two forces acting on the teeter-totter, it would go crashing down. So there must be a normal force being exerted up by the fulcrum in order to keep that from happening. Sorry, here I'm just going to make the force of gravity on the skinny kid less than on the big kid. Okay, so we've identified, so we've drawn our extend free body diagram so we can understand our forces. Now, the low-hanging fruit is to go ahead and write the force equations. What's going to be a little tougher is going to be writing the torques, and this is because we're free to choose our axis of rotation. So before we get into the weeds with that, let's just go ahead and write down our force equations. Yeah, we'll keep those in red, why not? Some of the x components of forces is 0. Well, there aren't any x components of forces, so that's not a terribly useful relation for us here. Some of the y components of forces is 0. Okay, so we've got the normal force acting up, Fg1, and Fg2 acting down. That has to equal 0. So from that, straight off, we can solve for the normal force. It'll be equal to Fg1 plus Fg2. So it'll be m1g plus m2g, or m1 plus m2g. So that's going to work out to be, he said that the bigger kid was 50 kilograms, the skinnier kid was 25 kilograms. Gravitational field strength is 9.8 newtons per kilogram. So the kilograms will cancel, we'll be left with newtons, and we will have 735 newtons. Great. So we figured out the force, the normal force from that. All right, now in order to figure out how far over we should put it so it's fair, we have to choose an axis of rotation. And here's the weird bit. When you're dealing with a system that's not rotating at all, you're actually free to put your axis of rotation literally anywhere you want, because if it's not rotating, it's not rotating about this axis, it's not rotating about that axis, it's not rotating about that axis, it's not rotating about this axis up over here. Whatever axis of rotation you care to pick, because it isn't actually rotating, is just as valid as any other choice. So I'll start by going with the one that most of us would probably initially think of, and then I'll show one that is mathematically a little faster. So for our take one, which I'll go ahead and do in purple, we choose to put our axis of rotation here. So if that's the case, then my R perp for force 1, so R1 perp, it's going to be 1 meter, and because the plank, or sorry, we don't know how long that is yet, it will be 1 meter. But the other thing we know is that whatever this distance is, it will be this distance here, the lever arm for force 2 off of this axis, R2 perpendicular, has to be equal to the length of the plank minus R1 perpendicular. And the length of the plank is 3 meters. So okay, with that, here let me copy paste this. Just so we can continue to look at it a little easier. There we go. So here we can go ahead and say the sum of the torques about this axis is 0. So first we'll look for the counterclockwise torque. So we'll have a counterclockwise torque due to gravity, and the magnitude of the torque will be R1 perpendicular times Fg1. The normal force does not exert a torque about this axis. Remember, we saw that if a force goes through the axis of rotation, the lever arm is 0, and so we can ignore it. All right. Here, this force is trying to make the teeter-totter swing clockwise, so that would be negative R2 perp FG2. All right. So we're solving for R1 perpendicular. FG1 is M1G. And sorry, this equals 0. And R2 perpendicular, remember, is the length of the teeter-totter, which you know, minus R1 perpendicular. Will be M2G. And that equals 0 again. Alrighty. So I can divide both sides through by G. G's will go away here, and 0 over G is still just 0. So interesting little tidbit that we can pick out of that is on any planet, anywhere, the game of teeter-totter is played exactly the same. All right, so let's follow this through. M1 times R1 perp. All right, so we'll have a minus M2L, and minus and minus means I'll have a plus M2 R1 perp equals 0. All right, I can group this M1 plus M2 R1 perp equals adding M2L to both sides. And so finally I get that R1 perpendicular is equal to M2 over M1 plus M2 times the length of the plank. We said the skinny kid was 25 kilograms. The not so skinny kid was 50 kilograms. And the length of the plank was 3 meters. So we get that the distance to put it so that the game will be fair is 1 meter away from the bigger kid. All right, let's copy this one more time. And now we'll do it with a different choice of axis. So there's never a wrong choice, it's just some are faster than others. So here, if we hadn't already needed to know the normal force, choosing the axis of rotation where we did would have been sensible. If we didn't need to know the normal force, putting the axis of rotation at the point of application for an unknown force will make the torque do it go away, and so then we don't need to know what it is. But in this problem, we were asked to find the normal force, so maybe it'll be easier for us if we make a different choice. So let's go pink this time. This time, since the problem asked in the first place, how far from the big kid should we put the teeter-totter so it's fair, we'll say this distance is still R1 perpendicular. But now, because my line of action for gravity is all the way over here, R2 perpendicular is just plain the length of the plank. So here's my line of action here. Shortest distance is R1 perpendicular, the thing I'm looking for. Here, the line of action is here. Shortest distance from the pivot is this, which is just the length of the plank. So now when I do sum of torques equals 0. Okay, now here, the torque due to gravity is the one that we will ignore. Because the line of action goes right through the axis of rotation. So the torque in this choice, the torque due to gravity, is 0. All right, do we have any forces that are trying to twist the thing counterclockwise around this axis? Yes, the normal force. So that'll be equal to, whoops, my bad. I thought I picked pink, there we go. That will be equal to R1 perpendicular, the thing that we want to find, times the normal force, which we already happen to find out. And then for things rotating us clockwise, that would be FG2. So it'll be R2 perpendicular, which is just equal to the length of the plank, times FG2, that equals 0. So R1 perpendicular is going to be equal to L times FG2 divided by N. So this is going to be equal to M2GL over N. So this will be 25 kilograms times 9.8 newtons per kilogram times 3 meters over the 735 newtons we found before when we found the normal force. Crank it through, you get the same 1 meter. So the two reasonable choices of putting your axis are either where if you've got a lot of forces you don't understand and they all happen to have lines of action going through the same point, then putting the axis of rotation there makes a lot of sense just because then the torques due to them are 0 and it makes the math easier. On the other hand, if the problem is saying to measure off from some specific point, it may be more convenient to go ahead and balance forces to figure out those unknown forces, just so you can ready-made plug in all the values and solve. So those are the two typical choices. Let's do a little more complicated example where things would be happening in 2 dimensions. So in this example here, I'm imagining hanging a sign off of a wall using a massless pole. And let's say the sign is out over here, and we'll just measure out to the center of the sign. Let's say the mass of the sign is 10 kilograms. You have a pivot right here. There's a hinge right here. And we'll say that the length of the pole out to the center of the sign is 4 meters. We'll go ahead and attach a guy wire to it such that it's attached 3 meters above the pivot. So yes, I am making the internal angles 37 and 53 degrees. Now, what I would like to know is the tension in the string, in the cable, and also how hard and in what direction is the normal force from the hinge. If you think about a hinge, the way a hinge is constructed, you've got a pin and then you've got like a follower over it like that. And if the hinge is having to exert a force to keep things from moving around, what will happen is the bit around the pin will make contact and you get a normal force right at that location. Alrighty. So we can go ahead, the system is just going to be the rod and the sign. So we can note the force of gravity is being applied there. Maybe let's switch colors for a sec here. Yeah, let's do that. Actually, let's even do this. Make that red so we can see the force well. There we go, except for you. All right, that's better. And then force due to tension on the sign plus massless rod is going to be directed like that. And then remember the system is the sign plus massless rod. there's going to be a normal force. I'm just going to point it in some random direction. I don't know the direction yet, so what that means is that we're going to have to separately think about the x and the y components of the normal force. All right, so with all of that, let's go ahead and balance the forces, and then we'll worry about the torques. So here, the sum of the forces in x has to be 0. What do I have acting on x? I have nx acting to the right, the x component of the normal force, which I don't know. The x component tension, well, that's acting to the left, so that picks up a minus sign. And the x component is going to be what you get when you multiply by the cosine of 37 degrees. So this will be minus t cosine 37 degrees. That'll equal 0. Okay, so once we find the tension, we'll have the x component of the normal force. Sum of forces in y has to also be 0. I drew the normal force and the y component of the normal force acting up. If I guessed wrong, it'll be negative. All right, and similarly, there'll be a component from the string that's acting upward, and there'll be a sign, so plus t sine 37 degrees. We have gravity acting down, minus fg equals 0. Okay, so far so good. Now the thing is, we have 3 unknowns, if you think about it. The normal, both the x and the y components of the normal force are unknown to us. Or if you prefer, the magnitude of the normal force and the angle at which it's acting are both unknown. Still 2 unknowns. And the tension is an unknown. So there's nothing we can do with this yet to make this any better. But we can go ahead and look at the sum of the torques. Sum of the torques equals 0. All right, now we need to sit down and think about where are we going to put our rotation axis. Now, you could put it anywhere you want, but I would suggest here that we put it at the hinge. And the reason I'm suggesting at the hinge is since we don't know the normal force at all yet. Even though we don't know what the normal force is, if I put the axis of rotation at the hinge, then that means that the line of action of the normal force goes through that axis, making the lever arm 0. And so then the torque about the hinge due to the normal force is 0. So then at least we can make that torque go away, and we can just focus on the tension and gravity. Now you could go about finding r perpendicular for the tension, and that would be fine. But here it might be instructive for us to remember that we could also write it as the tangential component of the force. Here the tangential component of the tension is going to be the y component of tension, which we've already worked out. That's t sine 37. And the tangential component of gravity is just plain the entirety of fg. So we can say then that our distance from the hinge out to these tangential pieces is 4 meters, so we'll call that our r. All right. So with that, we can now write that r times the y component of tension. That's trying to turn counterclockwise, so it's positive. And actually the y component of tension we said was t sine 37 degrees. Let's see, and then our only other torque, because we chose the axis so the normal force wouldn't contribute, would be a clockwise twist from gravity. That'll be r times the tangential component of the force of gravity, which is just the force of gravity. That has to equal 0. Okay, I can divide both sides by r, and I get that t sine 37 degrees is equal to fg, which is mg. So I get that the tension is going to be mg over the sine of 37 degrees. So this will be 10 kilograms, 9.8 newtons per kilogram over the sine of 37, which is going to work out to be 163 newtons, which is more than the force of gravity. And the force of gravity on a 10 kilogram object is 98 newtons. But this makes sense. It's not just pulling up, it's also pulling in. It's going to be compressing the rod a bit. Okay, so now let's start to figure out the components of this normal force. If we look at the y equation, if we look at the y equation for the forces, in fact, let's just copy that. And put that here. Okay. So if we look at the y equation for my forces, we've already worked out that the force of gravity was equal to t sine 37. That means these cancel. And so we get that the y component of the normal force is 0. So now we know that the force acts horizontally. In fact, it must be straight right. Okay. So now we can go back to looking at the x equation for our forces. Let's just give that a quick copy as well. So now we know that the entirety of the normal force has to be acting along x. So we can just replace that with n. Then we add t cos 37 both sides. We get the normal force is t cosine 37. So that will be 163 newtons times the cosine of 37 degrees, which is 130 newtons. So we get that there's a lot of compression happening on this rod. And it's also interesting that when it was all said and done, we worked out that the true direction of the normal force, there we go, that the true direction of the normal force wound up being straight to the right. Okay. I will close this with just one quick bit thinking about the stability of systems and how well they balance or don't. So let's say you've got a car that is making a dangerous turn or whatever, and you see the wheels pop off the ground. The concern is how much do you have to tip it before the car ends up rolling over? There we go. So there's the wheels there. So the question is it depends how low is the center of gravity relative to the wheelbase. So let's go ahead and mark in the center of gravity of the car. Like so. We've already seen that we can treat gravity as if it were being applied right here. The only other force acting is going to be the normal force of the wheel on this precarious bit of tire right there. Let me draw in some road just so we're clear on this. Now, let's say that the car is just about to tip over. If the car were just about to tip, as drawn here, the car would, the torque due to gravity about this axis right here would restore the car. But now let's say we're tilted just a bit more. Okay, I tried. Again, center. Oops. Yeah, still not doing good with that. There we go. All right, let's try it again. Okay, that's my tire. I'm going to need the CG to be right there. So now let's draw. Okay, yeah, that's better. All right, so here the force of gravity is acting straight down, and the normal force is acting straight up. Once again, I will choose this to be my axis of rotation. But now here, at this critical angle that the car is tilted at, oops, we can do a better job of drawing that. If it were tilted any less, it would be like this situation here, where it would flop back down right side up. If it were tilted over any more, then what's going to happen is it's going to flop the other way around and the car is going to roll over. So let's try to figure out what this critical angle is. So at this critical angle, and let me just draw in the vectors here just for clarity. At this critical angle, here is my axis of rotation here. This is my critical angle theta crit. We'll say that this right here is the height of the center of gravity off the surface of the car if the car were level on the ground. And we'll say that the width of the wheelbase is t. That would make this distance right here t over 2. Okay. Now, from that, we can work out that this here is also this angle here. So what we can say is that the tangent of our critical angle would be equal to the opposite over the adjacent, so t over 2 divided by h. Okay, so this will be t over 2h, just cleaning that up. And then we can take the arctangent of both sides. So what does this mean? What it means is the higher off the ground the center of gravity of a car is with in comparison to the wheelbase of the vehicle, the more likely it is to roll over. So this is why, for instance, it's usually easier to roll over a pickup truck than it is a normal car. As a pickup truck, because you set the suspension usually higher so that you have good clearance over, driving down twin tracks and stuff like that. That comes at the cost of the center of gravity being higher. So then this means that the critical angle will be less and the truck will be easier to roll over than it would be for a car that's designed to work on asphalt roads where you can set it down lower. This also, by the way, is why some designs of electric vehicles are basically impossible to roll over without like the use of high explosives or something. This is because the battery packs in a lot of electric vehicles are right around about half the weight of the car. And a fairly common design is, since you got to carry all that weight anyway, put it completely along the bottom surface of the car. By doing that, you can drop the center of mass of the car substantially, and so it sits a lot lower than it does, say, in a more traditional car where the engine of the vehicle has to sit higher off the ground than this battery pack does. So just fun little tidbit there. So the lower the weight to the ground, the wider the wheelbase, the harder it is to flip over. This is why you see racing cars, the drivers are basically sitting with their butts just barely scraping off the ground almost. That's just to get the driver as low in the vehicle as possible, to drop the center of gravity as close to the ground as possible, to make the car that much more stable. Okay, and with that, have a good one, and I'll catch you again in cyberspace.